Now we are back on YouTube.
Okay.
And now somebody decided to cut grass outside the window. Okay.
So.
Okay, so we're going to continue with the next talk of this Jürgens Fest. And it is an honor and a pleasure for me to introduce to Professor Dr. Albrecht Wagner. Professor Wagner began his studies in physics at the Munich University of Technology, and he received his PhD degree from the Ruprecht Karls University in Heidelberg. I'm very sorry for my German. Okay, he worked as a research assistant at the University of Heidelberg and also at the Lawrence Berkeley National Laboratory. From 1974 to 1986, he was a researcher at the German electron synchrotron. And from 1982 to 1999, he was a researcher at CERN. In 1984, he became professor at the University of Heidelberg. And since 1991, he has been a professor at the University of Hamburg. In that same year, he was appointed head of the research department at DESI. And in 1999, he was appointed chairman of the DESI board of directors. He is currently president of the University Council of the University of Hamburg. Professor Wagner, it's a pleasure to have you here, and please start your conference. Thank you.
Thank you very much for this invitation. I hope you can hear me. And let me start with observing that birthdays are always a moment of reflection and of looking back at what people have been doing, what oneself has been doing. So that is what I do, and it fits very well with the previous talk by Stefan Paul, who talked about the work in the framework of the thesis of Jürgen. So Jürgen, it's a pleasure to go back to the young Jürgen in Heidelberg and your early encounters with particle physics. So first of all, I will speak about what you did when we interacted in the group of Joachim Heinze, and then I will spend part of my talk in reflecting on the results which came out of these two experiments you were involved in directly and indirectly through your very early work in Heidelberg. These are the experiments JADE and OPAL, and then I will conclude. It has been said before that Jürgen comes from Stuttgart. And everybody knows this when listening to him. He doesn't speak what is called Hochdeutsch, but this very nice Swabian accent. And he's not the only eminent physicist who has this Swabian accent. I know several ones at DESI. And of course, also the former Director General of CERN has this slight trace of Swabian accent. So where is Stuttgart? For those who don't know Germany, you see here a map of the southwest part of Germany. You see the blue line there at the left, which comes out of a big lake. That is the Rhine River. And Stuttgart is here in the middle of it. Actually, this state is called Baden-Württemberg because it consisted out of Baden, which is the Black Forest, which is in the lower left corner, and Württemberg, which is Swabia, essentially, which is on the upper right corner. Now, Jürgen got his PhD, as we heard, in February 1992 at the Institute of Physics in Heidelberg. So where is Heidelberg? Heidelberg is here. It's where the Neckar, which is a river which goes through most of Württemberg, more or less flows into the Rhine River. Now the question is, of course, why didn't Jürgen stay in Stuttgart, which has a physics department, etc.? The answer is Heidelberg is simply a world-famous university. It's the third oldest university in the German-speaking part of Europe. The first one was Prague, which at that time was part of the Austrian-Hungarian Empire. The second was in Vienna, and the third one was in Heidelberg. All founded within a time span of 40 to 60 years. Now, Heidelberg is not only has not only a world-famous university, it is a beautiful town. There's even a musical, I Lost My Heart in Heidelberg. And this is the most famous picture, but there's another one which I want to show you, which is looking into the sunset of Heidelberg. And I show that because the sun is a little bit to the left of where the famous Institute of Physics is located. If you go the mountain ridge down, you see a little spike. I don't know what the spike is, but this is about where the Physics Institute is, halfway up from the river, and the street is appropriately called the Philosophenweg, the Philosopher's Trail. Heidelberg was and is famous for its physics. Bunsen was there, although he is probably more a chemist. Hermann von Helmholtz was in Heidelberg. Philipp Lenard, I come back to him. And the most recent Nobel Prize went to Hans Jensen, who is a theoretical nuclear physicist. Now, this was the institute in which all I am going to tell you took place. It is still part of the physics institute. It's still part of physics, but it's no longer an experimental institute. The experimental institute moved into the flatlands. But it was this building, which you see here, which was started in planning in 1907, was the first university institute which moved out of the old town into some quieter area. But the main reason, from what I know, was that the main street of Heidelberg, where most of the institutes were, had an electric tramway. And whenever the tramway passed, it led to wrong measurements. And therefore, the newly appointed director wanted to have a quieter place. So who was this man? It was Philipp Lenard, who received in 1905 the Nobel Prize, so the fifth Nobel Prize, for his work on cathode rays. That sounds actually very innocent, but he made a lot of basic discoveries of the nature of cathode rays, which are electrons traveling through an evacuated tube. He could have discovered the electrons, but he didn't. It was J.J. Thomson who did that. He provided Röntgen actually with his X-ray tubes. And if you look at the year when he received the Nobel Prize for his work, 1905, it was the year in which Einstein wrote his famous paper on the photoelectric effect. And of course, X-ray tubes played a key role in establishing the photoelectric effect. And it was Lenard who discovered that if you modulate the intensity of the irradiation of the anode, you get higher current, but not higher energies, which of course has to do with the way how the electrons are emitted. He came to Heidelberg from Kiel, where he was professor in 1907, and the new building was part of his hiring offer. Philipp Lenard has chosen the site for reasons I just described, and had considerable influence in how the institute should be built. Unfortunately, this brilliant career was not continuing. Probably, I don't know how his career continued, but his political inclination changed over the years, and he became after the First World War very anti-Semitic, politically radicalized, and then never wanted to accept the theory of relativity, and with another physicist, one probably known to you by the Stark effect, he founded Deutsche Physics, which opposed Einstein. So the sad ending of a brilliant career, but he was the founder of the institute. Now I show you a few of the directors of the institute. Philip Leonard I mentioned. Walter Bothe is another one, nuclear physicist. He got the Nobel Prize in 1954. And then other people who are famous, and the last one is Joachim Heinze, the one on the right-hand side, who was mentioned already by Stefan Pauer, and who was the thesis, one of the thesis supervisors of Jürgen. Now, the professors in 1991, when I left the institute, can be seen here. Joachim Heinze on the left, Gisbert zu Putlitz with glasses sitting, and Hans Specht with glasses standing, and myself. And I got this picture of the institute, this engraving, and they are looking at it at a typical celebration we had in the institute garden, which was famous for its celebrations. Now, what was special about Heidelberg? Heidelberg was very good in atomic physics, and later on in relativistic ion physics, but especially in particle physics and technology. I actually moved to Heidelberg because somebody said this is the best place to go. This was in around 1965 or so, and so experimental particle physics needs accelerators and needs detectors. In Heidelberg, there was a strong emphasis on the development of new technologies. For example, the already mentioned drift chambers invented by Heinze and his student Valenta. This picture, which was taken in Hamburg in 1974, shows the first cylindrical drift chamber at an electron-positron storage ring, the DZ Heidelberg experiment at Doris. And in order to do and build these detectors and the associated electronics with high precision, new electronic readout possibilities, one needed a big and capable mechanical and electronics workshop. Both were always very much encouraged by all the people coming to the institute, and this enabled us to build big and complex detectors. The detector development, as you will see in a minute with Jürgen's work, was also the ideal learning ground for students. This is a really very good combination, because it's difficult for young students, for example, an LHC experiment, to get experimental knowledge. And that, so if you do both a mixture of detector development and analysis, then you get that. Now, I showed you the first drift chamber. This is then the one which went into the JADE detector. It's called a jet chamber. And you don't see people on this picture, but you see people on the next picture, but the next picture doesn't show you the inner parts of it. So I show this for a second. You see at the back the reflection. It's about 2 meters diameter. And this is where the detector, finished detector, comes out of the institute on its way to Hamburg. And you see the detector just fitted the size of the institute. And every bigger detector then had to be assembled elsewhere. Now I come to Jürgen's diploma thesis, because it is interlinked with both the jet chamber in Hamburg and the jet chamber at CERN. The title was, and you can, the PhD thesis has been published twice, once in Helvetica Physica Acta, with the authors Peter Bock, the direct supervisor Jürgen, and Joachim Heinze, called The Measurement of Signal Charge and Charge Separation on Long Counting Wires with the DL300 Flash ADC system. And this was part of a work where several students were engaged. So Jürgen, I think, inherited his equipment from Manfred Zimmer, and then other people contributed. Peter Lennart was mentioned already, and Peter Bock was a professor is a professor at the institute. So what was this work about? It was about to see how you signal, I should say the drift chamber works on the principle the distance of the particle orthogonal to the wire is measured by the drift time. But where is it along the wire is measured by measuring the charge on both ends, and then as charge division proportional to the resistivity of the wire works also in a counter. It tells you then the position along the wire. And this technique had already been proven in Hamburg with an old electronics, but the flash ADC electronics has properties which we come back to later, which lends itself to more fancy and more performing detectors. And so there was a study, how do the signals look as a function of the Z, the longitudinal coordination. Probably the most dangerous thing about this rather simple looking experiment was that the outer tube, the outer skin of the tube was on high voltage. And so I was told there were many signs that one should be aware of this. Probably today one wouldn't be allowed, one would have to build a fancy interlock system. At that time, people were a little more nonchalant with this kind of thing. So the pulse shape, you see at each end of the wire, there is an preamplifier, then the signal goes to a flash ADC, which digitizes the signal and has a sampling rate of 100 megahertz. And the dynamic range, although it's 6-bit, it can be extended to 8 bits. And understand the goal of the thesis was what is limiting the Z resolution by charge division. And I show you only one signal, one result, and I took this out of Peter Bock's final paper on this, is that the resolution goes like 1 over the signal charge, which is not astonishing because there's noise and so on. So the higher the charge is, the better the resolution along the Z-axis. So you're interested in having large signals. So you see, this is a summary of Jürgen's early works, and you see how much he has published or presented. The studies of the digitalization he presented twice at the Frühjahrstagung, which is the spring meeting of the German Physical Society, which is an immensely important training ground for young students. They all have 10 minutes. They are exactly watched. After 11 minutes, the microphone is shut off, and it teaches them to give good talks. And it gave a talk at the seminar in Heidelberg and then published with the head of the electronic workshop a paper on this electronics. So let me finally say a few words about the flash ADCs. They were developed in Heidelberg, the high frequency flash ADCs for the use in the OPAL experiment. And the motivation was that you get a resolution independent of the drift time. And what a drift does is that the signal broadens the longer the electron cloud drifts. If you don't care about how wide the signal is because you don't have a threshold detector, but you see the pulse shape itself, the more independent you become of this drift time dependent resolution. You have an excellent double track resolution, and you have a better charge measurement because you measure the full signal. And just on the left, you see 2 early pictures which we took with a strobe oscillograph and the readout of the flash ADC, and you see how nicely the analog and the digital output coincide. And on the middle plot shows you 2 tracks crossing each other, and in the middle you have the anode wires. And on in the right-hand picture you see on the top and bottom the tracks which are still further apart, and then as they move together, at one point they really cross each other, so you only see one signal. And you can imagine if you do a line fit to these 2 signal shapes, you get a much better resolution than if you just have threshold measurements. And as this was a fairly new idea, we decided around the time Jürgen was in Heidelberg to install these flash ADCs on a trial basis in the JADE detector, which ran at the PETRA storage ring and was going to run a couple more years longer in order to get working experience. And this turned out to be very helpful. So I now come from something Jürgen did himself to what actually did we do with in terms of physics with JADE and OPAL by using flash ADCs. JADE started originally in 1979 and changed its jet chamber electronics, as I said, in the middle of the 80s to flash ADCs. The OPAL jet chamber was designed from the beginning with flash ADCs and much longer wires than in the case of the JADE experiment. So I will now make a kind of summary of highlights of physics, first at PETRA with JADE and then second with OPAL at LEP, in order to see what at that time, what was new and what was really, what were the interesting and hot topics of the time. Now, for those of you not familiar with Hamburg, PETRA was an electron-positron storage ring conceived in 73, 74. There were actually two competing designs, one in PETRA in Hamburg and one at PEP in SLAC. 1974, the November Revolution, the discovery of the JADE site took place, and so this gave the whole thing even more push and power behind it. The PETRA, and this one has to really appreciate PETRA construction. This is a ring with which you see is not a small ring. I forgot the exact circumference. It's over a kilometer. Started in 1976 and in 1978, 6 months ahead of schedule, the first beam was stored in PETRA. This is something which is, I think, stunning, even if viewed today. On the right-hand side, you see the classical cylindrical detector. The orange central, the light orange is the beam pipe. The dark orange in the center is the drift chamber, the jet drift chamber. Now, probably the most stunning discovery was the one of the gluon. Stunning because not only was it never in any of the proposals which were submitted to get the experiments approved, but because people had not really thought of that. So the one knew a lot of things, and I'm not going into the details since the 70s, but it was interesting that one had to wait for electron-positron colliders to really discover the carrier of the strong force. And in 1976, there was a key paper by Ellis, Gaillard, and Ross, which suggested that in strong interaction, you would have something similar to the Bremsstrahlung in electromagnetic interactions, which they call the hard gluon Bremsstrahlung, which should manifest itself in 3-jet final states. And this happens in the following way. You have E plus and minus annihilating and producing a quark anti-quark pair. And in some cases, and the probability for that is proportional to the strong coupling constant divided by the momentum, which at PETRA is about 10%. So with 10% of the cases, one of the outgoing gluons radiates, outgoing quarks radiates one gluon. And in some cases, of course, with a probability of 1%, 2 gluons radiate, and you get a 4-jet event. That looks seen by the jet chamber the following way. On the left-hand side, you see a clear 2-jet event. What you see is actually the traces of the particles, and what is the circular thing with the black dots in it. These are, each square is a lead glass block. So you see the lead glass impact of the energy in the lead glass. And the right-hand side shows you a typical 3-jet event with 3 particle clusters and 3 energy clusters. All 4 experiments saw these jets events. And to quote the the JADE speaker in the Lepton-Photon Symposium at Fermilab in 1979, quantitative as well as qualitative properties of the planar 3-jet events agree in detail with the predictions based on the Gluon-Bremsstrahlung process. This strongly suggests Gluon-Bremsstrahlung as the origin of planar 3-jet events. And this is really a very remarkable result. Other results I mention in passing because they're interesting. You always have interference between electromagnetic and weak interactions, and the closer you get to the Z production, the more influence the Z production plays. And this can be measured by looking at the forward-backward asymmetry of E+ and minus collisions. If you only had a photon exchange, you would have a perfectly symmetric curve, which is indicated here as QED. But if you interfere with the Z boson, then you get an asymmetric curve. You can use that curve and look at how does this asymmetry change with the colliding energy. And you see these curves which going downward, and you can derive from that an estimate of where the Z mass should be. This was before the Z was actually discovered, and you find a fairly good prediction out of these electroweak measurement, the interference between electromagnetic and weak. One of the top things, in a sense of important things one was looking for was the top quark. Unfortunately, we were far too low in energy. The theorists always predicted the top quark lies just around the corner. However, we went around many corners from 30 to 31.5 GeV, the top energy of PETRA, and we saw nothing. The cross-section or the ratio of the hadronic to the muon cross-section was 4 as expected from 5 quarks and QCD corrections. Okay, these were a few highlights from the JADE experiment. The same team which built the JADE was the nucleus for the OPAL experiment, which not very astonishingly looked also quite similar. And of course, that the goals changed, but I'm not going through them one by one, but these were the standard lab physics aims. Here you see the new size of the detector. This is the jet chamber. Actually, you see 2 former directors of labs on the right-hand side, although you don't see him really precisely. This is Rolf Heuer, and on the left-hand side, you might recognize my beard, although it was still not gray at that time. So this gives you just a feeling of the size. It's 4 meters in diameter. These are 2 events with showing 3-jet and 4-jet, or 2-jet and 3-jet events. And the very first measurement was really measuring the cross-section around the Z resonance and then linking it up with the earlier measurements from Doris, from PETRA, and later on one was adding also W measurements, and they just beautifully fit. Actually, this fit on about the absolute cross-section was used quite early to measure something which for which no measurement existed so far, namely the number of light neutrinos, light being with a mass less than the Z boson. And it required the absolute cross-section measurement. And you see here the error bars are actually increased in this plot by a factor of 10 to make them even visible. And the output is very impressive. It is 3 with an error of less than 1 percent. So that was one of the first very important measurements, because that influences a lot of the other theoretical predictions which come later. Unfortunately, I must say, every measurement one did at lab in all experiments agreed with the predictions of the standard model. So the standard model was tested at an unprecedented accuracy, but no deviations were observed. And we are still continuing in a way in this era. Also, LHC is not much better off. There are some hints in some corners, like magnetic momentum of the muon, which point to possible deviations. But it tells us something, these precision measurements, and we come to that now, tells us something about particles we don't directly produce yet. But to the electroweak tests belongs also the running of at the higher energies, like the up to 200, slightly above 200 GeV, which yielded a very, very nice measurement of the W mass. But here, this is one of two examples I show that the search for new particle got from these measurements at lower energy, one get very precise information about particles one did not directly produce, and these are the top quark and the Higgs boson. Because of these relations which you see here a plot as a function of time from 1990 to 2000, how the top mass was narrowed down. The first public presentation was made in 1994, just 1 month before CDF announced its discovery. And you just compare these two numbers and you see how powerful indirect measurements are. And that is important because that gives you confidence that the theory behind the standard model is correct and that you can trust these indirect measurements. Because then we come to the Higgs boson, and you see also what LAB has been doing in terms of its Higgs measurement. And now, so we knew that it was just slightly above the energy one could reach with LAB2, but not within the reach. And as we now know from LHC, it was just 25 GeV above, or 20 GeV above the energy one could produce at LAB. As we have seen with the PETRA results from the 3 jet events, one can actually deduce the coupling value for the strong coupling constant. This was then also done at OPAL, and here you see the combined results from LAB, PETRA, and Tristan, and this gives the most precise value for alpha S. Now, finally, I come to Jürgen's thesis, which of course was covered by Stefan Paul in a way which only he can do, because he collaborated very strongly with you, Jürgen. And but one sees, and this was also clear from Stefan's talk, one sees already your future research directions, which continue until today. Now, let me just come to the concluding remarks. In 1999, when I was on a business trip in Mexico City, Jürgen invited me to San Luis Potosí, and I gave a talk there, which I still remember was a very nice visit. And 2 years later, about the same time, I came to Zacatecas, and I don't know at which occasion these two pictures were taken. Unmistakably, Jürgen at the bottom directing where we should go next, smiling as he always does. And but I don't know what the pyramid is, but I think the other picture was taken at the same time. These are unfortunately together with the Cathedral of Zacatecas, which I don't know, have to show you are the only pictures I have from that trip. This was before handies were active and before one was taking digital photographs. So this brings me to my end. You have seen how directly and indirectly Jürgen has been of greatest importance in the group, and then in the two experiments I have mentioned, and of whom I have presented some of the results. the good understanding of the working electronics and how to do the pulse shape fits, how to interpret the pulse resolution and charge division, and then also the EDX measurements would not have been possible without the work, which was done in part before he actually, which were part of his diploma thesis and which were done published and in part of when he was already working at CERN. This was for him a busy time, but as we have heard, he doesn't shy away from busy moments. In the contrary, this stimulates him and this gives him new ideas. So, Jürgen, I can only wish you feliz cumpleaños together with stay as you are, vivid, energetic, full of humor, remain Swabian. That means also being thrifty with your money, but spending it where it is needed. And all the best for the future. It has been a pleasure to participate in your birthday. Thank you.
Oh, I have to thank you, Albrecht. Very nice presentation, remembering all these times working with the Heidelberg group. This was a great pleasure. Yeah? I also remember times when you had exams, oral exams, and I had to sit in with you during the oral exams. That's also something I remember. Yeah.
Did you learn something?
Yes, sure. Yeah, this was very nice. Maybe I should mention my involvement with JADE is even earlier, because I was summer student under the supervision of Siegfried Bede, and I worked in 3, 4, 5 JET events for the extraction of alpha S. This was my work as a summer student in '84 at JADE.
That's interesting, because I was wondering, I've seen that that you had a time as summer student, but I had nobody I could think of whom I should ask. So now I know. I should have asked
Bethke, yeah?
Siggy Bethke, exactly.
Yeah, and Jürgen von Groch, he organized all of that, yeah?
Yeah, Jürgen, I tried to contact, but he did. He probably has a new address.
Oh, okay. Yes.
Hi, Dr. Wagner.
Hello.
I'm Nora. Thank you very much for accepting to give a talk. It is a real pleasure to see you again.
Yes. Nora was also as a summer student at DC.
At DC, yes.
Great.
I may have a question.
Please.
It is with regard to the first part of your exposition, where you mentioned the work of Jürgen in the drift chambers. I used to have contact with and have many occasions talk with Valenta regard with the wire chambers. And I found very interesting that he says that there were some discussions at some conferences with Charpak, which was actually also announcing the discovery or the development of the wire chambers. And Valenta used to say that they had priority in that regard. Can you comment on this particular historical issue?
As well as I can. I know the question, and in going back to Charpak's original paper, you find in there indeed a mentioning of the drifting electrons, but as a deterioration of the resolution of a proportional chamber, not as something you can use to make the measurement. So Heinze and Valenta picked this idea up of saying, okay, let's make bigger distances than in proportional chambers and measure the time. So it required a more sophisticated electronics. So it was a totally different approach, although it used the same basic physics process. Now, I'm not an historian, so I can't say if Scharpak had in mind to build a drift chamber or not. It's certain that Valenta and Heinze built the first drift chamber. Actually, the first planar drift chamber was used in an experiment at CERN with Bogdan Poch, the KE2 experiment, K to electron neutrino, which is one of the rare decays which Heidelberg always specialized in. It worked very well, except for one day when Valenta wanted to inspect something and didn't realize the magnetic field was on, and so his stool on which he wanted to sit in front of the chamber was sucked through the chamber into the magnet, and the whole chamber was destroyed. But apart from that, it was working very well. And then the idea was generalized to cylindrical drift chambers, and that was the one I showed from the early DESY experiment, which was 3 layers of cylindrical drift chambers, which worked very well. Also in E+, E- environment, one was not sure that the background from the beam would actually enable one to measure with a drift chamber, but it turned out to work very well.
I can add there two anecdotes I have about the 2 drift chamber inventions, which were heavily discussed. Once we went to CERN with Joachim Heinze, and in the evening we had a beer together in the CERN Restaurant 1, late evening. And he made one remark, and he told me, never speak too loud in the CERN cafeteria. This was an advice Joachim Heinze gave me. Yeah? And the other thing, is, when I was at, no, this was not, at some conference, I met Riegler, I think is his name, from Vienna, who organized the wire chamber conferences. And he told me that for the first wire chamber conference, he invited Heinze and Scharpak to give talks and to see if they can agree on something. And he said the publication of the proceedings was delayed by 9 months because each of them refused to cite the other one. And so they had to wait a little bit to resolve that problem. Yeah?
That's interesting. I remember this wire chamber conference. I think I have somewhere also in the publication, but I didn't know about this delay in publication. And
yeah.
I didn't know. Yeah.
But you know, Valenta used to say that there was a conference, probably in Poland. I don't know. I remember exactly when it was, where it was. But Valenta used to tell me, a student of Heinz, and he was working on the wire chambers. And then he went to the conference and gave a talk on the issue. And he used to say that Scharpak was sitting in the conference. And after the conference, then Scharpak probably went back and started working hardly on what he was probably doing. But Valenta used to say that somehow some priority should be given to them when in this regard. So I think there must be some documentation which would be interesting to review and see the timing was in the development of the wire chambers.
Yeah.
It's also interesting because you can prove publications, etc. You can't prove what somebody, even if somebody was at the conference, can also pretend that he was not at that meeting, at that talk, for example. So it's very hard to prove. I trust Valenta here more. I think he is honest about this. I think there was various, I mean, nobody disagreed with Valenta's, Scharpak's invention, but and also the fact that Scharpak had understood what the resolution was limited by. but he didn't make the next step, and he didn't see it from a system point of view, that you could actually be much more economic, although your individual electronics is more complicated, but you get 2-hit resolution, you get fewer channels, but more performing. What I've shown about flash ADCs, you can never get in a proportional chamber. And so that's why proportional chambers, except for some very targeted use, left a place for drift chambers. So history has spoken a word here, and it's clear that Valenta and Heinze and the group around them, there was also the electronic guy who Farr, who appears in one of my slides, who invented and built together with other people the appropriate electronics. Schürlein was a guy who was at that time in the group, and so it's a team, as you know. I mean, I don't need to tell you that the success of these things are teamwork, and you need the right players in order to win. And in that sense, I think for me the situation is clear that the drift chambers were brought to particle physics by Valenta and Heinze.
So there is another, so between the two, between Heinze and Charpak, there was still later also, when they met each other, some tension. I remember a meeting in, was 87 probably, when we made a proposal to upgrade the omega ridge, what Stefan talked about. There were actually two proposals. There was one proposal from Charpak's group, and then there was one proposal by the Heidelberg group. And so there were two presentations, and the design criteria, the properties of the two solutions were presented, and both of them were present. Even they didn't give the talks, but Heinze and Charpak were sitting in a small room together, yeah, and it was high tension in that meeting, yeah. But finally, it was agreed that our design was better, yeah.
Good. I'm happy for you.
Yeah.
Well, I think we have to cut now. Dr. Wagner, it's been a huge pleasure to have you here. Thank you very much for your presentation. Let me tell you, Jürgen, that in the YouTube transmission, you have several congratulations for your birthday. And Dr. Wagner, we invite you to stay if you want. We still have 2 more talks. In a few minutes, Augusto Sechuchi will be connected. So thank you very much. Thank you very much to you all.
Thank you, and a nice celebration. I don't know if I will stay, but I will look at the other talks later on your YouTube link. I think that is possible.
Yeah. That's very good. Thanks again, Albrecht. It was pleasure, very nice from you.
All the best to you.
Thank you.
Bye, everybody.